let me begin by saying that
Oh, in the newer, yeah, you're right. In the newer paper.
Ramanujan generally likes to shock treatment to people, including Hardy. So his mathematics is definitely startling, but he startled others not just by the nature of the results, but also by not revealing how he had obtained these things. So one of the things that he used to go and show his teachers, so let me call this Ramanujan's outrageous claim. So one of the things he showed his teachers was, okay, so this was a statement he would go and show one of his teachers. They made this great discovery. Now, clearly, any respectable college teacher would say this is, totally crazy. You got a divergent series, and you're, simply saying that this is equal to minus 112. It's not as crazy as it looks, because what you can do is, we may think of, so it is not as crazy as it looks. Because we may view 1 plus 2, we may view the series in 1 as formally zeta of s, but at minus 1. So zeta of s is summation 1 over n to the s, which of course we know is converted only in sigma greater than 1. But formally, if in this series I put s equal to minus 1, I end up with this. So you may formally think of the sum of the positive integers as zeta of minus 1. Now, we know from Riemann's functional equation that the Riemann zeta function can be extended to be a meromorphic function in the entire complex plane. So the question is, what is the value of zeta at minus 1 coming from this analytic continuation? Okay, so we know that zeta s can be analytically continued to all of C. What is then the value of zeta minus 1? The answer is it's minus 112. So exactly this value that Ramanujan had. Okay, so it turns out that zeta minus 1 equal to minus 112 as Ramanujan claimed. So the point is this: Hardy says several times that Ramanujan did not really have any idea of the theory of functions of a complex pair. He of course knew complex numbers. He knew Euler's formula for the sine, e to the I theta is cos theta I sine theta. He used series for trigonometric functions, product representations for sine, and so on and so forth. But he did not really have any full grasp of the methods of the theory of functions of a complex pair. So for example, Hardy said he never really knew Cauchy's theorem or how to use Cauchy's theorem. So he definitely did not have the idea of the functional equation of Riemann or how to do the analytic continuation of zeta s, but how did he arrive at this correct value? And in fact, I'm going to show you a method, Ramanujan's method, after we convince ourselves that zeta minus 1 is minus 1, but using Riemann's functional equation. And one of your homework problems, which I'm hoping tomorrow morning I have to be at home waiting for a Sears guy to come and do a repair. So I'm going to write up your homework set. So one of the homework problems will be to use Ramanujan's outrageous method to show that zeta of minus 2 is 0. We know that the Riemann zeta function vanishes at minus 2, so use this method to actually show that 1 squared plus 2 squared plus 3 squared is equal to 0 by his method. Okay, so we'll talk about his method in a moment. But now, let us compute some special values of zeta s using Riemann's function equation. Okay, so computing special values of zeta s using the functional equation. So by the way, this is one of the reasons that when Ramanujan wrote to Hardy, he said, the local mathematicians are unable to understand me in my higher flights. So he was confident that something like this was actually correct, but the local mathematicians did not understand what he was saying there and why he was making this assertion. Okay, but before we get to that, let me introduce a function for you. Okay. So define beta of s to be pi to the minus s over 2 gamma s over 2 zeta s. So this is the function which satisfies beta s equal to beta 1 minus s. But notice this function is not entire because it still has a pole at s equal to 1. Gamma half is square root of pi, and therefore this part is finite at s equal to 1, but zeta still has a pole. So what we do is define this and C of s, which is s minus 1, beta s. So the s minus 1 has been introduced so you want to multiply by s minus 1 to clear the pole, but if you still want to retain the symmetry s goes to 1 minus s, then you have to multiply also by s, so that you've got s minus 1 is symmetric under 1, s goes to 1 minus s. But interestingly, we introduce a factor 1/2 here, okay? And the reason for this 1/2 is that s over 2, gamma s over 2, becomes gamma of s over 2 plus 1. Otherwise, you've got to carry this 2 along in many computations. So it is better to clear that by putting the 1/2 right here. Okay? And note that two properties. One, C of s is now entire because the simple pole of the Riemann zeta function has been removed. Of course, you will say, what happens to the poles of the gamma function? Remember, those poles of the gamma function have been wiped out by the zeros of the Riemann zeta function and the even integer. The poles of the gamma function and the negative and the non-negative integers is cleared by the zeros. So C of s is entire, and not only that, C of s is C of 1 minus s. So we'll be working with this function C, it's entire. So for instance, if one wants to have a product representation, you have that for an entire function in terms of the zeros, right? This is from complex variable theory. With the Hadamard product representation, we can do that for C of s. Right? And then of course from that we have a representation for zeta s. And this is also another reason why in your treatment of the gamma function, you're going to emphasize the product representation of the gamma function. So if you know the product for psi and the product for gamma, then you know the product for zeta apart from this. Okay, so C of s is entire, and we have this. All right, now we state a theorem here. So the theorem, the first part was what we have, okay? Theorem 1 for today, so part 1 and 2 as I have. But then I'm going to say here, the third part of the theorem is that C of s is real for real s. And the fourth part of the theorem is that C of s is real for real s and for sigma equal to half. So on the real axis, the function C is real, plus on the half line, the function c is also real. Okay, so it's real valued on both. And then finally, I'm going to say here that for c naught equal to c half equal to 1/2, and that implies the Riemann zeta function of 0 is minus 1/2. This also I will explain in the context of Ramanujan's philosophy. All right, so let's prove. Well, first of all, from the definition of C, okay, so how is 2 and 3? What do we know about the Riemann zeta function? Well, the Riemann zeta function is given by this convergent series in real part S positive, greater than 1. And the series is a positive term series on the real axis beyond 1. So it's clearly not just real, it's positive. Between 0 and 1, the Riemann zeta function is defined by that integral with the fractional part. Remember, we did an analytic continuation of the Riemann zeta function in terms of the integral, where we replaced integral part of x by x minus fractional part of x and so on, and then utilize that. But that integral is real valued, and 1 over s minus 1 is real valued on the real axis. So we now make a point saying that from the series representation of zeta s for sigma greater than 1, and the integral representation of zeta s for 0 less than sigma less than 1, actually we can put less than or equal because of 1 over s minus 1, we see that zeta s is real for s greater than 0 and s not equal to 1, of course. At s equal to 1, it's infinity. Consequently, C of s is real for s greater than 0. S is not just real part. And that follows from 2 and 3. Okay, good. Now, what about C of 0? All right, by symmetry, C of 0 is the same as C of 1. Right? C of s is C of 1 minus s. So let us just go with the definition of C of 1 in 3. So C of 1 in 3 is 1/2. This s minus 1 I will attach to zeta s. So I'll put s minus 1 zeta s evaluated at s equal to 1, which means in the limit. Okay? And then I have pi to the minus half, gamma half. That's C of 1. But now we do know that the Riemann zeta function has a simple pole at s equal to 1 with the residue 1. That means if I multiply by s minus 1 and put s equal to 1, the limit, that is 1. And then I have pi to the minus half, and gamma half is the square root of pi. So this is 1/2. So C of 1 is C of 0 is 1/2. All right, but now let's look at C of 0. C of 0 is, they should yield zeta not equal to minus half. C of 0 is, now there you will see the use of s over 2. we will look at S over 2 gamma S over 2 evaluated at S equal to 0. Don't go directly and put gamma 0, that becomes infinity. But I've got an S which is a 0, so I attach S over 2 at S equal to 0. Then I have a pi to the minus S over 2 is 1. All right, then I have a zeta 0. And then this is going to give me a minus 1 at S equal to 0. So that's really what we have. Okay, but this product is gamma of S over 2 plus 1 evaluated at S equal to 0 multiplied by zeta 0 multiplied by minus 1. But now this is easily evaluated at S equal to 0. This is just gamma 1. And gamma 1 is 0 factorial equal to 1. So this is simply minus zeta 0. And zeta 0 is, and this is known to be half. So zeta 0 is minus half. Okay? That's the value of the Riemann zeta function. 0. This will be useful later. Now, what can we say about zeta of minus 1? So we always go to the Xi function. Okay. So, next, note that Xi of minus 1 is the Xi function at 2. Okay, S goes to 1 minus S. Now what is the Xi function at 2? 1 times 1 times beta of 2, which is pi to the minus 1. Gamma of 1 multiplied by zeta of 2. And so I'm going to use the fact that zeta of 2 is pi squared over 6. So we use that. And so we end up with 1 over pi times pi squared over 6. So that is pi over 6. So we use zeta of 2 equal to pi squared over 6. So Xi of minus 1 is pi over 6. But what is Xi of minus 1? So let's go to Xi of minus 1 here. Minus half. Oh, sorry. Yeah, that's okay. So if I do S over 2 with gamma S over 2 and call it S over 2 plus 1, then at minus 1 this gives me gamma of plus half instead of gamma of minus half. Okay, so you end up with gamma of half. And now S at minus 1 gives me minus 2. And S at minus 1 gives me pi to the S at minus 1, right? So square root of pi, right? And then multiplied by zeta of minus 1. But this here is pi over 6. And that's the square root of pi, that's the square root of pi. So I get pi, I get a minus 2, I get a zeta 1, and that implies zeta of minus 1 minus 112. So the value of the Riemann zeta function at minus 1 is minus 112. So this is really coming out of the Riemann functional equation and analytic continuation. Now let us see Ramanujan's argument. So how did he arrive at this? Okay? So Ramanujan's it's not a full proof, but it's sort of a reasoning. So how did he arrive at this? So Ramanujan's proof goes as follows. And there is sort of a method behind this madness, really. Okay. So he says, put 1 plus 2 plus 3 plus 4 and so on as equal to C. Well, that itself is a wrong stop. I mean, this C is infinity, but he is treating it like, let it have a value, let it have a finite value. So let 1 plus 2 plus 3 up to infinity be equal to C. Therefore, 4 times 1 plus 2 plus 3 is 4C. Now, why did he choose 4? Why couldn't he have chosen 16? Why couldn't he have chosen, 24 or something? Okay, there is a reason for this. Okay, so this is now equation 4. Okay. Recast 4 as follows. You write 1 plus 2 plus 3 plus 4 equal to C. Now this 4 times 1 plus 2 plus 3, 4 times 1 is a 4, and I write it below the 2. It's important where you write it, where you put it. So the 4 is placed below the 2. 4 times 2 is 8, and he places that below the 4. Now let's put a 5 and a 6, and then you'll see what happens. 4 times 3 is 12, and he puts that below the 6. So this is 4C. Now, he says, subtract 1 from the other. That already is wrong, because I've got 2 divergent series, and you cannot just subtract term by term, but Ramanujan does it. So this is one of the interesting things that you have to keep in mind. Euler also, at that time, there was no real formal theory of series and convergence and epsilon and delta techniques and so on. I mean, that all came with Cauchy later. So Euler also did manipulations. But the formal manipulations that he did, even on infinite series and so on, without paying too much attention to convergence, were always correct. So this is one of the great things about these geniuses, is that when they wave their hands, it turns out to be actually correct. So they have some feeling that what they're doing is correct, even though it's not entirely rigorous. So in the case of Euler, there were no mistakes at all. Ramanujan made some mistakes. Okay, so for example, his assertions on prime numbers was definitely, there was mistakes, and in fact Hardy says there his limitations were clearly seen, because the theory of prime numbers, you cannot just be guided by intuition. I mean, you need more than that. And so that he marks as perhaps Ramanujan's one great failure. And interestingly, in this movie, the opening scene when Ramanujan meets Hardy in his rooms, Hardy's first comment to him is, your statements on prime numbers are wrong, and this is why they are wrong, which of course Hardy did point out to Ramanujan, actually even in a letter in response to Ramanujan. But in the movie, there is a lot, it's probably emphasized far too strongly that Hardy was critical of Ramanujan in his methods and proof. He definitely showed where Ramanujan was wrong, but he was never as critical as emphasized in the movie. In fact, in his writings, he says, while it was clear that Ramanujan did not have a full grasp of proofs, many things that he did were correct. And I had to point out where he made mistakes, but I did not want to, what did he say? He didn't use the word overemphasize. I have the exact quote in my article. He didn't want to sort of ram it into him, because he said, I did not want to destroy his enthusiasm and his inspiration, because he was such a fertile pupil that I really didn't want to sort of overemphasize this. So it's quite the opposite that's being shown in the movie. Anyway, so he writes it this way. And now he says, so by taking the difference, see, a lot of steps in Ramanujan's crazy proof. In 5, we get 1 minus 2 plus 3 minus 4 plus 5 minus 6 and so on is equal to minus 3c. So the point is, I mean, this is still as crazy as the earlier one, but why was Ramanujan putting emphasis on getting this alternating series as opposed to the original? Now this fact you saw already in Ramanujan's proof of Bertrand's postulate, where he takes double the thing and he subtracts. Go back to your notes. Theta of x over 2 times theta of this, and he does this subtraction. So this is a game that he plays consistently and correctly. I mean, he always ends up getting the correct result. So this is minus 3c, all right? Next, consider 1 minus 2x plus 3x squared plus minus 4x cubed and so on. Now this is a familiar series in calculus.
What?
And this is 1 over 1 plus x whole squared. But this is for absolute x less than 1. We know, after we have gone through all this epsilon delta, that this series representation is valid only for absolute x less than 1. So what he says is, in 7, just replace x by 1 on both the left-hand side and the right-hand side, which means he is taking the limit as x goes to 1. But you can take the limit of x goes to 1 of this, and that is the limit of x goes to 1 of this, but the limit of x goes to 1 of this is not the quantity obtained by taking the limit of x goes to 1 as every term, because it's not uniformly convergent as you're going to 1, so you cannot interchange that. Okay. So he says, replace or put x equal to 1 in 7 to conclude that 1 minus 2 plus 3 minus 4 is equal to 1 quarter. But minus 3c equal to 1 quarter, and therefore c is minus 1 quarter. Now, if you remember my discussion of summability, Cesaro summability, I threw in something called Abel summable. So Abel summability, you push an x in here, evaluate this to be some finite quantity, and then go to the limit as x goes to 1 of that object. Whatever value you get, you say that the series is Abel summable to that value. It doesn't mean the series converges to that value. So let's put a remark here that this means 1 plus 2 plus 3 dot 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 equal to, not 1 minus 2 plus 3 minus 4 is equal to 1/4 Abel summable. See, but Ramanujan was not using summability. He was just saying this is equal to that and that's equal to this. Okay, so prior to Ramanujan, there were people who had tried to assign finite values for series which are blatantly divergent. But they knew that this finite value is a formality obtained through a summability process and not through actual convergence. But Ramanujan asserted this as the value. But it's remarkable that this sort of crazy technique gives you the minus 112 that you get by the functional equation of Riemann. Okay. Now, I think it is Abel who said, if I'm not mistaken, divergent series is the work of the devil, and anybody who plays with it will be doomed to failure. So you can't just play with divergent series. You got to be very careful the way in which you deal with divergent series. And so in particular, he got this idea of summability of this sort of divergent series. All right, now let's look at the 1 minus 1, zeta 0. There's Ramanujan's crazy formula, work at s equal to 0. So does our method work at s equal to 0? We'll just test it. So what is 1 plus 1 plus 1? Equal to zeta 0 formally. Now, zeta 0 is minus half. So now what we have to do? So we got to put Fowler and Ramanujan. Put 1 plus 1 plus 1 equal to C. Now I want to get 1 minus 1 plus 1. I mean, that's the Ramanujan philosophy. Replace the series by an alternating series. So to get minus 1 after subtraction, you multiply everything by 2. So that's 2C. Therefore, 1 minus 1 plus 1 minus 1 dot 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 is minus C. See, this is very interesting. He is not saying if this is C, technically minus of 1 minus 1 all the way should be minus C. Already there is something wrong. But if you follow the Ramanujan crazy argument, 2 plus dot 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 is 2C, and if you subtract, you get this. Now you put x equal to 1. And that is 1 over 1 plus x. And now you put x equal to 1 in 8 to conclude that 1 minus 1 plus 1 minus 1 is 1/2. But this is really almost summable to 1/2. Therefore, 1 plus 1 plus 1 is minus 1/2, because that's your C. This is your minus C, sorry. That's your C. That's the zeta 0 equal to minus half that we obtain. So there's no mistake. I mean, Ramanujan finding out the proper value. So he always found out these things, whether or not he knew these fancy theories. He always gave the right value. Okay. So this is really what happened. I mean, there was this course on elliptic functions and integrals given by Berry. And anytime Berry would write down a definite integral, he would turn towards the audience, and Ramanujan in the audience would provide the value of the definite integral.